morning, students. Welcome to this next session of Module 3. Today we'll be seeing about oscillator and the clock, which we are using in the 8051 microcontroller. Right? So we'll see 8051 microcontroller has an oscillator and a clock. Right? So this, what is this clock? The clock generates the clock pulses to which your all internal operations are being synchronized. So the clock frequency, based on the clock frequency, what frequency is the clock, that will be used for the generation of the clock pulses. Based on these clock pulses, your instructions are being synchronized. What instruction has to perform, this is being triggered, this is being initiated with this based on the synchronization of the clock pulses. You can see that we have already learned the pin diagram, right? There we have the two pins which are Xtal1 and Xtal2. Right? These are connected for the resonating circuit as we are showing it here. You can see that here we have the resonating circuit which is being connected, that is using two capacitors and the crystal here. Right? So using this, we are connecting this to the Xtal1 and Xtal2, which is pin number 18 and 19. In 8051, the manufacturers, what they have done, they have designed the oscillator circuit such that we can use our frequency, we can vary the frequency from 1 megahertz to 16 megahertz. Right? So that is what is the manufacturers they have designed. So we can use our clock frequency from 1 megahertz to 16 megahertz, and based on this, all the instructions are being synchronized. We'll see the next one. What is that? What is the clock frequency? Say if I say clock frequency is F, right? So if the clock frequency is F, then the smallest interval of time, that is the reverse of clock frequency, is called as the pulse, or the pulse width, which is denoted by P. Within the smallest frequency which is possible, which is generated, is F, then the reverse of that is called as the pulse, right? Two such pulses define each state. Now, how can I say that? See, this is what is the clock, which is supposed if it is generated, right? So two pulses will be equal to one state. And what is a state then? State is a basic interval where discrete operations of a microcontroller are performed. What are those? What kind of discrete operations? It could be a fetching of an instruction, or fetching of an opcode, decoding of an opcode, executing and writing. If I divide my overall execution phase or fetch phase, what is that? I can if I divide my overall execution of an instruction of any opcode, what all are the different phases included is, first I need to fetch the instruction, right? Suppose say add instruction or a move instruction. I need to fetch the instruction. Once the instruction is being fetched, I need to decode, right? I need to say whether it is a move instruction or a add instruction or whichever instruction it is, right? Once it is getting decoded, then I need to execute. Say if it is a add instruction, I need to execute, I need to fetch the data, and then I need to execute it. Once it is getting executed, I need to store back the result. So these are the different phases of an execution of an instruction. So that basic phase will be taking is called as the state. That is, if I say I have two pulses, two pulses together, I form it as a state. Like that, I have states which are formed like state 1, state 2, state 3, state 4, right? You can see it here. We have different states formed. This is what is about a state. What is a machine cycle then? A machine cycle is made up of 6 such states. If I have one machine cycle, I'll be having 6 states. Together, 6 states together is called as one machine cycle. What is a machine cycle? The smallest time interval to accomplish any simple instruction. If I am taking any simple instruction, the simplest could be with only registers involved or the accumulator involved in the instruction. So that is what is the simplest instruction. If it is a complex instruction, then it is being divided into simple instructions internally, and those will be executed. Right? So this is what is about. What is that? We call it as states, pulses and the different machine cycle. Right, now we'll see the next thing. What is, if I have one machine cycle, how many states I'll be having? 6 states. One machine cycle is equal to 6 states, and each state is made up of 2 pulses, right? So in that way, if I want to calculate one machine cycle, that will be equal to 12 states, correct? One machine cycle is equal to 6 states. Each state is made up of 2 pulses, so hence one machine cycle is equal to 12 states, right? So that is what is I have quoted here again. Then if I want to know, this is the prerequisite. What is whatever we have already studied. We have already studied this in the module 1, right? How your clock is connected and all. Now the added thing in this video is, what is the number of what is a pulse? How many pulses together we call it as a state, right? 2 pulses is equal to 1 state. Then like that, some 6 stages together, states together, we call it as 1 clock cycle, right? So this is what is a added thing in this video, in this module 3. Now next concept is like how to calculate the time taken. If I want to calculate, how to calculate the time taken for any instruction to get it executed. So what time it takes, what is the duration of execution of any particular instruction. If I want to know that, so what is the formula I'll be using? T instruction is equal to C into 12D by the crystal frequency. As I told, we can use the crystal frequency from 1 megahertz to 16 megahertz. Whatever the crystal I'm using, based on the crystal's frequency, I'll be calculating my instruction. And what is the C? C is the number of machine cycles it is taking to execute a particular instruction, right? So how let us take one example. I have to take a I have to find the time taken to execute add a comma r1 instruction if the crystal frequency is 16 megahertz. I want to calculate what the time taken to execute this particular add a comma r1. This is one of the instructions which we use normally, right? I want to calculate what is the time taken to execute this. How will I know that? For which we have in the appendix, we are given with what is called as mnemonic is given, the description of that, and you can see that in the right corner we have here how many bytes are taken when we are using that, right? Suppose if I'm saying I'm using add a comma r rr, that is rr will be ranging from R1 to R7. We know that, right? R0, R1, R2, R3, R4, R5, R6, R7. Completely R0 to R7. 8 registers are included in, are being referred as RR. Capital R suffixed with the small r. If I am saying add a comma r, right? It is taking 1 byte. And how many cycles it is taking? Cycles here is machine cycles. How many machine cycles it is taking? 1 machine cycle. Like that, we have different variations of add here. Add a comma the address, that is the memory location. Because it is a memory location, right? It is taking 2 bytes, but the execution is of only 1 cycle. You can see that all your add are taking 1 cycle only for the execution. And you can see decrement, DAA is also taking 1. Decrement is also taking all the decrement instructions are taking 1 cycle. Divide, you can see that it is taking 4 machine cycles. Why is this? Because divide A, B, how does it work? A has the dividend, B has the divisor, and once it is being divided, what will be there after division? At A you'll be having the quotient, and in the B register we'll be having the remainder. So we are storing back 2 values after the operation, because of which the writing of the data after your execute phase, the write will take 2 more cycles. Hence we'll be using here, it takes here 4 bytes. Even multiplication, you can see multiplication also takes 4 bytes, 4 machine cycles. Why? Because again after multiplication, A has a multiplier, B has a multiplicand before I multiply. A and B I'm multiplying means A has a multiplier, B has the multiplicand, either one, right? And then I'll multiply. After multiplication, A will have the higher value, B will have the lower byte, right? So this is what I mean, sorry, A will have the lower byte, B will have the higher byte of the product. whatever the product I have, if I have a product of 16 bits, then the first lower 8 bits will be there in the accumulator, the next higher 8 bits will be there in the B. So again we have two registers to be written, so it is taking again here 4 machine cycle to execute that, right? So you just have to note all these things, right? Even increment, you can see all increments are taking one machine cycle except increment DPTR. When I say increment DPTR, it's again is of DPTR is of 16 bits, so it will take 2 machine cycles. Like this is the table continues, where you can see you have your subtract here, right? Later if you see the next one, we'll see the next, even the logical operations are all listed. If you see the logical operations, you have your and, you have your what is called as, one second, I'll clear out all this. Yeah, and, right, or, XOR, clear, right? We can see that there are different logical operations which are being listed, among which if you have any address, right? So see this here, this particular XOR address with the N. This is what is the operation description. How many bytes it takes? It takes 3 bytes of to store. It is taking 3 bytes. I have to store this particular XOR with the address location comma hash n. I have to be storing this in a 3 bytes of area. And then how many cycles it takes? It takes 2 machine cycles to execute, right? Likewise, we have this one also. Wherever we have both the destination and the source as the number, address is also means a location, memory location. Say I can say this as ORL 30H comma hash 45. What is the meaning? 45 is moved to the location 30, right? So 30 is also a 8-bit data. 45 is also 8-bit data. ORL is also opcode, is also of not 8-bit, but it takes 1 byte. So together it becomes a 3-byte, right? So it is a 3-byte instruction. If it is 3-byte, obvious that I need to be using 2 cycles, right? Here also ANL. You can just note, other than this, all our logical instructions are taking only 1 clock cycles, right? Except where we have both source and destination as 8 bits. This is also 8-bit. This is also 8-bit. Then we'll be using, that will be consuming 2 bytes of machine, 3 bytes, and then it will be taking 2 machine cycles, right? So we'll see the next set where we have the move instructions, right? You can see that we have different move versions. We have push and pop also at the last, exchange also. And you can go through this table. I'll be forwarding this PPT to you. You just have to note how your move is being used, how different versions of move, how many bytes it is taking, how many clock cycles it is taking. All these things you need to note, right? Next set is call and jump instructions. We have E call, L call, right? Yeah, as we already know, A call is taking how many bytes? You can just see A call will be taking 2 bytes and the execution cycles are 2. Even L call also, it takes 2 bytes only, but it will be taking it will be taking the 2 machine cycles, but it will be using 3 bytes to store, because L address is of only 16 bits. This L address is only 16 bits and L call is taking 1 byte. S address is of 1 bit, that is 8 bits, 1 byte, and A call is also of 8 bits, so that is 1 byte. So together this will be 1 byte and this is 1 byte, together it is 2 bytes. L call also, this is 1 byte. L address, that is a long address, is of 16 bits, that is 2 bytes, together it will be 3 bytes. Like this we can see that it is of 3 byte, but it is taking 2 cycles to execute, whereas here also it is of 2 bytes, but it is taking 2 cycles to execute. And you can even see DJNE, CJNE also, right? CJNE, you have different versions. All will be taking 3 bytes to store, whereas it is taking 2 machine cycles to execute. Even all we have 2 versions of DJNZ, that also is taking 2 machine cycles, right? S jump, L jump, everything is there. All are taking 2 cycles. So we can see that all our jump and call instructions, even the return and return. Why return is taking 2 bytes here? 2 machine cycles. It is taking 2 machine cycles because when we say return, we are returning from a subroutine. If I say return I'm returning from an interrupt, right? In both the cases, I am popping out two top values, two top stack values. Why is that? Because I'm using a address there. I have to pop out the address which is of 16 bits. If it is of 16 bits, obvious that I need to be using pop operations which is of 2 times, because a stack is 8-bit operation where we are popping out 16-bit data. Hence we are popping out twice, which will take 2 machine cycles, right? So that is what is about the call one. This is like in terms of how many clock cycles it is taking, and you can see all our jump instructions are taking conditional jump, unconditional jump, right? Return instruction, all are taking 2 machine cycles, right? You have already seen that we are using we are taking we have listed here that all our jump instructions are taking 2 machine cycles, right? So that is what is this about call and jump. Next we'll see the next one, next set, which is the Boolean expression. In the Boolean expression also you can see that we have some instructions which are of 2 cycles, which consumes 2 cycles, some instructions which are of 1. Wherever we have logical instructions like A and L, right? Or L, that is R and or instruction and and instruction, and operation and or operation will take 2 machine cycles, correct? Whereas if we see the clear, right, clear A or clear C, right, if I do that, it will be taking only 1 cycle, 1 machine cycle it is taking. Like this, we need to be knowing how many machine cycles each instruction takes. And what is this last column here? The last column here, it is what is the flag which is getting affected when I am using this. When I am using A and L, that is AND operation. If I'm using, and you can say that this is a bit operation, not byte operation. These are the bit operations. If I'm using this bit operation, I can see that A and L, C comma B means I need to AND the bit whichever I am mentioning here with the carry flag, right? So because I'm using here carry flag, my carry flag is getting affected, right? So in the list of the flags getting affected, because I'm using here carry flag, the carry flag is getting affected. And because this here also I'm using C, so this is getting affected. Wherever I'm using my C, right, there my C flag is getting affected. That you need to note, right? And you can even note that in the previous this is about Boolean, right? We can see the previous ones also. Wherever I'm using jump instruction for instructions like CJNE and all, these are, what is the CJNE's internal operation? It has to internally subtract A and address, or A and the direct value. Because I am subtracting and I'm not storing the result, where only the carry flag is affected, right? So whether the borrow is required or not, based on that, if I require a borrow to subtract internally, then carry flag is 1. There is no borrow, then carry flag is 0. So based on this, the carry flag is getting affected. So like this, I'll be listing the next one. So you can see that move instructions, no carry flag is affected, right? No carry flag is affected for move instruction. For all the logical byte operations, the one which we saw previously was the logical Boolean operations, that is with the only one bit. Here we can see that this is a logical operation which is of byte operations. No flags get affected, right? But for the arithmetic operations like add, decrement, increment, subtract and all, there are many flags which gets affected, right? Like we have your carry flag, overflow flag and auxiliary carry. And based on all these things, we can even refer these flags to make some decisions, whether after addition overflow has occurred or not, whether I got a carry out of addition or not, whether the auxiliary carry is there or not. Based on all these things, even we can make some decisions, right? So this is what is the last column, which will give you about information about which flags are getting affected. So this is what is the last column. The point to be noted here is we should be knowing what all instructions will take how many clock cycles. So we are concentrating main on this column, the fourth column. That is what is the number of cycles each instructions are taking. How many ever instructions we have listed here. What is the point we are noting here is how many bytes it is taking to store on the memory, and how many clock cycles it is taking when I am executing it, right? The main concentration is on the column number 4, right? Now once we have noted this, as we go on, as we get the things along, we'll be coming to know which instruction will take how many cycles, right? So we'll go back to the previous slide where we were seeing about what is the time taken for add a comma r1 instruction, right? So if I want to know this, I'll go back, just see add a comma r1 is there, right? Add a comma r1 comes in the first one, where how many cycles it takes, it takes only one machine cycle, right? So if I do that, I'll go back again. So add a comma r1 will take only one machine cycle. So here C becomes what? C is equals to 1. So if I want to calculate T instruction, which is the formula is T instruction is equal to C into 12 divided by the clock frequency. The clock frequency given here is 16 megahertz, right? So because of which it is 16 megahertz is equal to 1. Why 1? The C is 1. It is add instruction is taking only one machine cycle. Hence 1 into 12 divided by 16 mega, which is equal to 0.75 into 10 to the power of minus 6, which is 0.75 microsecond, right? So this is what is the time taken for executing one instruction, which is add a comma r1. Like this, if I want to say instead of using 16 megahertz, I have used 12 megahertz, right? What is the time taken for execution? The time taken is called as period, correct? The machine cycles period. What is the period of machine cycle? One and the same. Time taken to execute and period of machine cycle is one and the same. Now what is that I'll be doing here? Instead of 16 megahertz, I have used here 12 megahertz crystal. Then what is the change I need to do? Instead of C into 12, instead of 1 into 12, I should be using, I'll just repeat the formula, which is C into 12 by the crystal frequency. This time C is equals to 1 and the crystal frequency is 12. So what will be the value? If I calculate the value, what will be the value? T is equal to C into, where C is 1. So 1 into 12 by 12 mega, which is equal to 1 microsecond, right? Likewise, if I use the next frequency, which is very important, why I have highlighted is, this is what is the clock frequency which we are using in our microcontroller. Our microcontroller uses this crystal frequency is 11.0592 megahertz is the frequency which our 8051 uses. Now if I use this as a crystal, right, crystal frequency is this, then what is my value? Instead of here C into 12 by 16 mega, I'll be using what I need to do, what I'll be using here, I'll be using T equals C into 12 by 11.0592 mega, which is equal to 1.085 microsecond. This is the period. You should remember, this is very important. This 1.085 microsecond is the period of machine cycle for 8051, whatever we are using for next all calculation, until unless it is not mentioned with any other frequency. The default frequency, the crystal frequency, default crystal frequency we'll be using is 11.0592 megahertz, for which we'll be getting the period of machine cycle as 1.085 microsecond. You should be knowing the calculation about how did we get this 1.085 microsecond. Right, that was the period. Now what is the other thing we'll be noting is, if I know the period, how should I get the frequency? It is reverse of, that is inverse of the period is the frequency. 1 by the period is equal to the frequency. We'll calculate that. If 16 megahertz is the crystal frequency, what is the machine cycle's frequency now? It's reverse. There we did 12 by 16 mega. Here, what is that we are doing? We are doing the reverse, that is 16 megahertz is the crystal frequency. And why did we take 12 here, by the way? Well, because each machine cycle is using 12 states, right? So only it is 16 megahertz by 12, which is equal to 1.33 megahertz. If the crystal frequency was 16, if the crystal frequency is 12 megahertz, then it is 12 megahertz by 12. Hence, it is 1 megahertz. Right? In a similar way, the important point to be noted: if we are using a crystal frequency of 11.0592 megahertz, then what is the machine cycles frequency? Then it will be 11.0592 mega divided by 12. We'll be getting 921.6 kilohertz. Right? So if we are using a crystal frequency of this, then my frequency of a machine cycle is equal to 921 point, it should be 1 or 6, almost the same, right? 0.1 kilohertz or 0.6 kilohertz. So this is what is the frequency if I'm using the crystal, which is 11.0592 megahertz, right? Let me clear out the, yes, yeah. Now we'll take one example where I am writing here I am writing one of the programs, right? If I take one of the programs, what will be the number of the bytes it is taking and number of clock cycles it is taking, right? So here if I say I want to move 34H in 3 registers, that is R5, R6 and R7. I want to store 34H in 3 registers, R5, R6 and R7. If I want to do so, what is that I'll be doing? I'll be writing instructions like, say, move R5, 34H, R6, 34, R7, hash 34. And what is that? A simple program. What I'm doing here is I'm just taking out things like how many bytes it is taking and what is the number of clock cycles it is taking to execute this, right? So if I want to calculate that, see, if it is move R5, hash 34, where does it lies? Move, it comes in this, right? Move R4 or R5 with hash n. N here is 34, right? If I take that, how many machine cycles it is taking? How many machine cycles it is taking? One machine cycle, right? So if I say it is one machine cycle for this, one machine cycle for this, one machine cycle for this, so totally it is taking 3 machine cycles to execute this this set of instructions, right? So number of machine cycles is 3 is equals to 3. C is equals to 3. Then my t in, that is the time taken to execute this set of instructions, is 3 into 12 by 11.0592 mega, which will be equal to 3.255, not milli, it should be microseconds. Right? It should be, this is the number of the cycles which it is taking, right? If I take the next one, this is also, we need to calculate how many cycles it is taken. So I have already checked it. It is taking it, C is equals to 4, right? So instead of 3 here, I need to put it here 4, right? And calculate. So this is what is the next step. The next same program I have written it in this way. The second method is where I've moved A with what? 34, right? And I'm using that with the, I'm using A to move the data to the R5, R6 and R7, right? Because of one instruction has increased, the number of clock cycle also has increased, right? You can see that. And the last method I'm using is move R5, hash 35 and move 6, 06, 05. What is happening? What is there in 05? 05 is, that is register R5. It is having 34. I'm moving it to 06. Why I'm using this? Because both registers cannot be used. I can use one location and one register, or both can be locations. You can see that move 06, 05 is of 3 byte instruction. Why it is of 3 byte? Opcode is of 1 byte. This 06 is also 8 bit, that is 1 byte. 05 is also of 8 bit, that is 1 byte. 1 byte plus 1 byte plus 1 byte, it is a 3 byte instruction. If instruction is of 3 byte, it will take how many clock cycles? It will take 2 clock cycles to execute. Hence here you can see that we'll go back and check also what is the number of clock cycles it is taking, right? Move. If I click here, right, move, I can just see that move address comma address, right? Yeah, this one, right? If I see move address 1 comma address 2, it is taking 3 clock cycles, and it is it is taking 3 bytes, and it will be consuming 2 clock cycles to execute that, right? Whereas if I use other than the previous ones were all, right, less only. But here again move R5 comma hash 34 is also how many cycles it takes? It will take here uh, 1 clock cycle, whereas these will take 2. This is taking 2 clock cycle. This move is also taking 2 clock cycle. Only the first one is taking how many clock cycle? 1 clock cycle. So together it is 2 plus 2 plus this one is 1, right? How did I get that? After I look into the table, right? I have to look into the table. So this is taking 1 machine cycle, this is taking 2 machine cycle, this is taking 2 machine cycle. So totally I'll be having 5 machine cycles for this particular program. So and hence my period will be 5 into 12, right? 5 into 12 by this, so it is 5.425. What is the point to be noted here is the same concept of moving 34H to the 3 registers R5, R6, R7 is written in 3 different ways, right? It is written in 3 different ways or 3 different methods. You can see that this set of instruction which is used is taking only 3 machine cycles, and the time consumed is 3.255, whereas the next set is taking 4 machine cycles and the time taken is 4.34, and the last method, if we use the number of clock cycles is 5 and it is taking 5.425 seconds, right? So what is the difference here is you should be writing a program in a optimal method or optimal instruction should be used to reduce the number of clock cycles it is taking, right? If I am taking less number of clock cycles means what? I'm executing my program in a faster way. So among these 3, this method, whatever we have written to write or to move the data 34 to these 3 register is the optimal. Why? Because it is taking less time. Am I clear with this? So this is what we are I wanted to say in this particular slide, right? If I take any program, if I write any program, you should see that the number of instructions, number of bytes it is taking to store should also be less, and also the number of cycles it is taking to execute is also to be noted. You can even note one more point. The total number of bytes it is taking in the first method is 6 bytes here. 6 bytes are used to store the program, but the number of clock cycles are only 3, whereas the second method the number of bytes are reduced, right, from 6 to 5, right? 1 byte I have reduced here to store the program, but the number of clock cycles is 4. Based on your memory you can choose this. Based on the speed I can this is not the optimal one, right? This could be the one which we can select, or this program I can write if I want the execution speed to be increased. If if speed matters, this is the one. If memory matters, then this is the one, right? So this is what is based on how all our programs requirement is there. Program is to be optimal in terms of speed or optimal in terms of memory, right? Based on this you need to be selecting, or you need to be writing your program. We'll go for the next program again, where I have told for 8051, this is also a sample example from the textbook only, right? For 8051 microcontroller system, the crystal frequency is this, which I have already told. It is not changed, it is the same one. Find how long it takes to execute each instruction. So in the previous slide, I had taken only one instruction and different clock frequencies I had given. In this question, clock frequency is the same. I'm using different instructions here, right? move I'm using, decrement I'm using, DJ and Z I'm using. How many clock cycle it takes, based on that I'll be calculating the period, right? How long it takes, is the period we need to calculate. So if to know that, we already know that move r3 comma hash 5 5. So this is like of the form move r comma hash n, right? It is move r comma hash n. Yeah, this is the one, right? If I want to choose, this is the one instruction format, right? Where it takes one machine cycle, right? So it is taking how many machine cycle? It is taking one machine cycle. So if I have to say, then like that only I can even select the next one, which is the decrement, right? Whereas decrement comes in the arithmetic operations, right? Yeah, decrement takes again one clock cycle, right? The next instruction was decrement only. See, decrement takes again one clock cycle. DJ and Z, I had already told how many clock cycles it takes. All the DJ and Z will take two machine cycles, right? L jump and S jump, right? These also will take two machine cycles only. We'll just see with this, right? All my DJ and Z will be consuming. See, you can just see these are the DJ and Z, right? If I take through, you can see that all my jump instructions, all the jump instructions are taking two machine cycles, right? You can see that all the jump instructions are taking two machine cycles, right? So without any confusion, if it is L jump, S jump, A call, L call, or any CJNE, DJNZ, or any conditional jumps return, you shouldn't bother. You shouldn't just make sure that all the jump instructions are taking only two machine cycles, right? That is important. We are taking all the jump instructions along with the return I and return will also take only two machine cycles, right? So make sure that, keep that in your mind. That will help you to calculate what all the required things are there, like period, or maybe period, or the clock frequency, right? Both will be using the number of machine cycles, right? So for which, if I use that, so I'll be using DJ and Z, L jump, S jump, all will be using how many clock cycles? Two clock cycles. And NOP uses one clock cycle. And you already have noted multiply will be using how many clock cycles? Four clock cycles. I have explained why four also, right? So we'll see how to solve this. I should be knowing the basic period. The basic period is 1.085 microsecond. I should be writing this first. Always write this first and then calculate the different things, right? So for that, the basic period is 1.085 microseconds, right? I'll list out the different machine cycles. For instruction A, it is taking one machine cycle. 2 also one machine cycle. For C, D, E, all are jump instructions. It is taking two machine cycles. NOP is F, right? It is taking 1 and multiply is taking 4. Based on that, it is 1 into this basic, 1 into basic, 2 into this. I'll be getting these values. Am I clear with this? So this is the basic thing which we need to know. Why I'm using these things, why I'm concentrating on machine cycles, right? And why, how to calculate the values of the period or the frequency of a machine cycle. If instead of period is asked, like here the question is how long it takes to execute each instruction is given. So for which you need to calculate the period P. If it was asked like what is the machine cycles frequency, then it should be reverse. That is 1 by 1.085 microsecond you need to do, where we'll be getting 921.6 kilohertz, right? So that I'll be using to calculate that. So normally frequency is not asked, will be asked with the period only, right? So we need to know all this things. So what all we learned in this session, we learned what is the clock frequency and what is exactly how the clock frequency is getting affected when we are executing the program. What is a state, what is a machine cycle, what is how many states will form a machine cycle, right? In one machine cycle I'll have 12 states, hence I'll have 6 states and 12 pulses. right? Each machine cycle is equal to 12 pulses. Hence, in our calculations, we'll be having this 12, right? So only we have written here the overall frequency. I mean, if I want to find the T instruction, C into 12, right? This 12 is because of that only, right? And then what is the formula to calculate the period? Is T instruction is equal to C into 12 by the clock frequency. All frequency, normally default it is 11.0592 megahertz unless it is changed, right? So this we need to calculate, for which the basic period is 1.085 microsecond. This is the basic period for the frequency, which is 11.0592 megahertz. Based on this, whichever instruction is given, right, that instruction's machine cycle we need to know, right? How will we know? We need to be knowing, we need to refer that table where you have listed the opcode and the number of machine cycle it is taking, that you need to note. So that will give you the number of clock cycles it is being used. Based on the number of clock cycles it is using, I'll be calculating the time taken or the period for the execution of that particular instruction, right? So this is what is required. This is a prerequisite. Watch this video for the next session, whenever we take. This all will be helping you out to know how to calculate the period for any instruction.